Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today, what's on the menu? Two shapes, graphs and cubes. So we are going to finish on graphs, what we've started last week, and then I'll show you everything about data cubes, right? I need your attention. Thank you. All right, so in terms of graph databases, we basically have the labeled property graph, which is one of the two data models. And the second model that I finished on is the triple store model. The triple store model is based on the idea that you abstract away a graph as a huge collection of triples. And every triple consists of, you guessed it, three parts. The first one is called the subject, the second one is called the property, and the third one is called the object. Every one of these triples actually represents an edge, right? An arrow in the graph from the subject to the object, but it's annotated with a property. And so if you have billions or trillions of such triples, you can basically on the logical level reconstitute the whole graph. So this is an alternate model. In fact, this belongs to the world of the W3C, so the standard maker for the web, XML, and so on. And so I finished by explaining to you that you know that in W3C, everything is a URI. We love URIs there. And so the subject, property, and object very often will be URIs. Note that a URI is just an identifier. So you can say, ETH is located in Zurich, and then you have a URI for ETH, you have a URI for is located in, and you have a URI for Zurich. But we saw that you can also use numbers or strings or atomic values instead of a URI, right? For example, if you say ETH has 20,000 students, then you would have ETH as the subject, number of students as the property, but then the object would be a number. It would be 20,000, right? So it wouldn't be a URI in that case. And the third possibility is that you can also have blank notes, right? If you don't want to give a name to a subject or an object, you just have a blank note, and you can use that, for example, for the land on which ETH is located. You just say it's located there. You can also attach it with more properties, but you don't give it a name, right? So URIs, literals, and blank notes. For whom is that clear? Right? So that's the beautiful world of triple stores. Now, the interesting part about triple stores is the syntax. Now, we didn't see any syntax for the label property graph, right? You just ETL it into the system by creating nodes and edges you can import. And that's it. But in the case of triple stores, there is actually a syntax. In fact, there is not a syntax, there are plenty of syntaxes. But that's not new to you, right? There's also plenty of syntaxes for trees. There's JSON, there's XML, there's YAML, and so on. And the point at which you start calling a syntax yet another something probably already shows that there's already a lot of them. But we don't have yet another graph syntax yet. Maybe one day we'll have that. So instead, we have an XML flavor, we have a JSON flavor, Turtle is kind of original, and many others. But I'm not going to show you many details. I just want to give you a feeling of what it looks like. First, Turtle is probably the most popular one because it's actually quite simple. So let's take a look at what's happening here. So basically, you list your triples. That's basically what you have in the syntax. One line has one triple. And you can see that every triple has this subject, property, object, right? Now, there's a trick because we are lazy. You know, we're computer scientists. We are paid for being lazy. You will be paid for being lazy and optimizing things. So what about reusing the subject or reusing a property? Well, that's easy. If you want to reuse the subject and the property and basically add them again on that line, you just put a comma in there and just repeat the object. So that's how you associate multiple objects to the same subject and property. And if you add a semicolon instead, then it means you only reuse the subject, but then you specify again a property and an object, right? So you can see it's very easy to read. And then if you put a point here, then that's a period, that's the end. And then you continue with more triples. So if you don't want the comma and the semicolon and you don't want to be lazy, then just put dots everywhere, but then you have to put subject, property, object every time. Just as a quick hint, because you might be surprised, because I told you it's URIs, and now I'm showing you Q names, right? You recognize Q names. For some reasons that I have no idea about, don't ask me why, the people in the RDF community, they don't use QNames at all in the same way as in XML for some obscure reason. So basically what they do when they see what otherwise would be seen as a QName in XML, they just take the URI corresponding to the prefix, that would be this one. Usually it ends with a sharp, but what they do, don't scream, they take the local name and just concatenate it with the URI. So basically when they see ETH:self, for them, it's not a QName, it's actually also a URI that is obtained by concatenating the namespace here, followed by exactly that. So it's basically eth.ch/sharp self. Then you have example.com/geography sharp is located, or sharp population. That's the reason why they put a sharp here. You know, a sharp is a fragment in URLs. So this is why they put the sharp, because they expect that it's going to be concatenated with the local name, right? This is just unique to the universe of RDF. Just be aware of it. So this is why here I'm telling you that these are actually URIs because of that. Right? But in XML, they are still QNames, right? Okay, so who is with me? All right, so this is the simplest syntax. Now, just for completeness, I'm showing you the others, but very quickly. This is the JSON LD syntax. It's also made of triples. And basically, the way that this is done is that they group everything by subject. So every time they have a subject in the @ID field, ETH:self, that's the same rule as in here for the concatenating with the URI. Then again, with the same rules, they have the properties, and here they have property object, property object, property object. They just share the same subject. That would be the equivalent of the semicolon, basically. And then you just create more and more and more objects for every subject. This is the JSON LD syntax. And then in here, you have all the prefix namespace bindings. All right, that's the JSON syntax. There is also an XML syntax. It looks like this. They basically have this, there is a schema, of course, for the namespace RDF right there. And then they list, again, you have a property and an object, a property and an object, a property and an object. They're also grouped by subject, and the subject is here in the about section. This is really the same thing, right? You have a subject with multiple property objects, and here again, a subject with multiple property objects. And then if you want more subjects, just repeat the RDF descriptions as many times as you want with a different subject in there. That's the XML syntax. To make the matter worse, technically in XML, that's supposed to be a QName, but again, when they parse that, after parsing the XML document, they take all of the QNames and also do the concatenation with this, right? Again, a lot of people would scream seeing that coming from the XML world, but this is how it's done, right? So don't be surprised if you see this. So this is why in the context of RDF, triple stores, this is a URI, this is a URI, this is a URI, this is a URI, this is a URI. Only this is a literal, right? In that case, it's actually a literal. Okay, who is still with me? Who got scared by the use of QNames in RDF? Some of you. Okay, that's okay. That's I am too. I really wish that they would have used QNames, but this is how it is. All right. Okay, but this is just syntax, right? From the moment that you have parsed it, you know what happens with syntax, right? We parse it, and then it's in the memory, and we forget about the syntax. Once it is in the memory, there's just URIs everywhere, and that's it, right? Then it's super simple. Okay, I'm almost done, right? And again, I'm quickly skimming through it because we are not going to go into the details of that. You know that we need a language every time we want to query a model, right? So in the case of labeled property graphs for the Neo4j database system, we have the language called, what's the language called for Neo4j, yes? Cypher, exactly, that's the Cypher language. And we have also one for triple stores, it's called Sparkle, not to be confused with Spark SQL, right? Sparkle, and Sparkle queries triples. So you can see it looks just like SQL because again, whenever people design a language, they just have to make it look like SQL. So there you go, select, where, order by, and so on. And here you see they use these question marks for their variables, just like we have dollars in JSONic, we have question marks in there. And here you see some sort of patterns, right? You want some variables or something, whatever it is, we call it S, located in Switzerland, that delivers a bachelor's diploma, and that has the name. We just also give it a name. We are just going to find out when we get the results of the query. You see that this would be the equivalent of, in the Cypher language, these ASCII art patterns, right? When we have these rows going and so on. So this is a bit the equivalent with the labels here, which are properties in triple stores, but they would correspond to edge labels in the labeled property graph, right? So we look for this pattern. These are the constraints in the where clause. And we are going to return, that's in the select clause when you have a language like SQL. So S and name. So we will get as many of them as there are matches. So obviously you will expect ETH to appear in there. We are probably also going to have EPFL, all the Fachhochschule and so on. So anything that matches this pattern. So it's a list. In that case, what you get actually would be a 2-column table, right, technically. Order by the name, if you want to even order alphabetically by name and return the top 10. So that's not new to you, right? This is just regular SQL. Right? So this is it. This is Sparkle. And again, you know, I focused a bit more on Cypher last time, but I can tell you, you want to learn Sparkle, is going to be very easy. Going to be very easy because of everything you already know about SQL, about JSONic, about tuple streams. There's always the same idea of flowing from clause to clause, passing tuples. It's always the same ideas. Who feels, just as a feeling, that you would learn it without too much effort? Right? A lot of you, very good. That's exactly the goal. And in fact, it applies to everything. There's many other languages for trees, others for graphs. There, for example, I think they call it PGQL, which is Oracle's language for graph. It's going to be very easy for you to learn as well. By the way, we'll have Oracle people tomorrow for a guest lecture. We'll tell you about data shapes and how they see data shapes. All right, so that was Sparkle. So you see, we now have Cypher for label property graphs, Sparkle for triple stores, PGQL, Gremlin is yet another language. I love this name. And there's many, many, many others, right? And of course, there's many other technologies. So I would like to mention Apache Giraffe or Giraffe. I'm not sure how it's pronounced. We have GraphX, that is an Apache Spark library. So it works on top of Apache Spark, but you can query graphs. I'm not showing it to you, but I'm sure you could also learn it very, very easily now. PGX is Oracle's graph database, and PGXD was the first ever sharded graph database, I think, in the world. They were the ones who managed to shard a graph database, which is a very difficult problem. But they solved it, and then the other providers, Neo4j, they also introduced sharding and so on, right? Sharding, in fact, you see now you can also understand what's in the news, but who follows, you know, blockchains, proof of work, proof of stake, Ethereum, little bit? So you probably heard that the Ethereum blockchain introduced sharding, right? At first, it was not sharded at all, meaning you really have the same data on all the machines. But the moment you introduce sharding, the idea that you partition the data, you can basically scale up a little bit more, right? So the idea of sharding in the Ethereum blockchain is exactly the same idea. All right, that's actually my last slide for graph databases. Any questions on graphs? Should we continue to cubes? More enthusiasm, cubes, yeah? Okay, let's continue. Yeah, okay. So let's stop.